What is this? Okay, so we were talking about programmable logic. Programmable logic array. I don't know, something is wrong with this touch screen. You had a class today morning before this? No, you don't have any classes these days. And I heard that you all didn't found what data structures difficult because we kept 2 extra classes for you. I don't know how many attended the extra classes that we kept. No, I heard this from faculty that your data structures was all bad because of our extra lectures. I don't know how many people. I never get the entire strength in class. Now, who are those people who suffered so much because of the extra classes? What, you will get extra marks? Ah, yeah, yeah, possibly. Okay, fine. Let's. It's not working well. Okay, anyway. My lines are all going crisscross. I don't know what is happening. Okay. So here, suppose if I have, you remember what I spoke about programmable logic array that we have, it is, you have the AND array, you have an AND array and an OR array. Both, you can actually, both are programmable. Now, what I mean by programmable, I will just draw the AND gates and show what internally happens. Okay. Suppose if I have, okay, so I have 3 inputs. My functions, I have 2 functions, f1 and f2, which are functions of inputs x2, x1, and x0. Okay, so in that case, if I have three inputs, okay, I can have my x2 can be x2 or x2 bar, which goes as the input. Same way, x1 can be x1 or x1 bar. So I will have totally 6 connections for each of my AND gates. Okay, 6 connections are there. Okay, now suppose if my first product term is going to be a function of x1, in that case there will be a connection established like this. Okay, like from x1 I take a line and then there is a connection established. Similarly, if x1 bar I do not have anything, the line comes like this and it stays open, there is no connection. The next line again I have for x2, then the connection is made. Similarly, wherever I have a connection, only there this kind of, it's like fuse wire. You burn the fuse wire, you make a connection inside internally. I'm just talking internally what it will look like. Okay, so I can make connections according to what product term I want. This product term P0, if I call it P0, is going to be according to what connections I have given. It is x2, x2 dot x1 dot x0 bar. Okay, that is a, so depending on what terms I need for it, I will be taking, the connections will be made appropriately. So then so same way for the next gates. Okay, so next, if I have it here, the first one is not connected, means it goes like this itself. I'm taking x2 bar and x2 bar, then I might not have any connection here and here. X3 I connect. So this is my P1, means this is x1 bar and this is x0. In this way, randomly we can connect. I mean, depending on what function I want to implement, I can connect. Why is it going like this? I really have no idea. This is getting, okay, fine. So one more connection. I'm randomly giving the connections. It's not that there is a specific reason why I give. So x1 dot x0. I'm not able to draw properly. I don't know. There is something wrong. I'll call those people. By the time they come, half the lecture will be over. Now, so you have to connect it this way so that. So this is how internally connections are made, depending on what function, what product term I want. Last class I told you we do some minimization depending on what function I want to implement. So if I want a function to be implemented corresponding to each of the inputs, there a connection will be made to the AND gate. So AND gate has, because I have x2, x1, x0 in their complemented and uncomplemented form, each AND gate has a total of 6 connections, which we can make or not make. Okay. So whichever is required, the first term P0 has x2, x1, and x0 connected. So there I have only those connections are made. The rest of the lines are open. Got it? So that's how it's done. Now, this is only the AND part. Now, I also have the OR section. Connected, it's a single line. I think I have to. Okay, so you give the wires like this. I have two functions, f1 and f2. Now, okay, so suppose if I say f1 is equal to p0 plus p1. In that case, the connection from p0 and from P1 will be made and P2 will be not there. Okay, this line is not there. So this is how it will look. Let me just go. Okay, and similarly you can connect F2 is P1 plus P2. I am saying it is P1 plus P2. That means your P0 does not have a connection, it's open. P2 will have a connection made and this has a connection made. Okay, this way it will come. What a bad. Just give me 2 minutes. Let me just call. Is this clear? Okay. So we can make connections. That is, so when we draw, we usually do not draw like this. We will draw just as the AND gate, whichever connections we will tap. So how I actually will draw this thing is, which we already drew earlier, x2, x1, according to the previous page, my P0 was x2, x1, x0 bar. So x2. So wherever x2 is there, from there I take a connection. x1, x0 bar. x1 bar, x0. x1, x0. And I will give one more term. I am using one more term, which is so I have 4 product terms here. I'm just generating 4 product terms: P0, P1, P2, and P3. And here is F1. F1, whichever terms I'm using, I can put it there. F2. So this way we just show connections. This is how we will largely show. The previous figure was to show you how internally a wire connection is there. So it is just that those connections are kept open. When we are drawing as a PLA, we will just show which all points we tap connections from for each product term. Okay. So this function F1 is a function of P0 plus P1 according to what connections I have made, P1. And this is a function of P2 plus P3. So this is PLA, where we have a programmable part for our AND array also and a programmable part for our OR array also. Now, we also have something called somebody drawing. वो ये जो है ना देखो अब मैं लाइन ड्रॉ कर रही हूँ यहाँ से ड्रॉ कर रही हूँ तो ऐसा
मतलब प्लस करना है
हाँ
आपको।
और वो टच भी कभी कभी ना
प्लीज।
उसके साथ ये लाइन से कोई प्रॉब्लम
ओके,
नहीं कहाँ दिख रहा है
कैलिब्रेशन
कहीं और से
क्लियर
आ रहा है
कैलिब्रेशन नहीं।
क्या ना चैनल
आपने सेव किया हुआ है?
नहीं मैंने सेव नहीं किया और मीटिंग चल रही है I see the scope for an extra class now. Huh? Can we go? Can we go home? No, no, no. This will be fixed. But the time I lose that, I have to take another class. That's what I'm saying. Who's? The faculty is here, no? Everyone wants that. Yeah, yeah, yeah. I believe it.
रिस्टार्ट करना पड़ेगा।
Restart ना तो वो मीटिंग एंड कर दो।
क्लोज ही कर देगा।
So we have another kind of a device. It's called programmable array logic. Okay. Programmable array logic, this part, what happens is that I have a programmable AND array and a fixed OR array. Okay. So what we saw earlier was programmable logic array where both were programmable. My product terms and my sum or the function generated, both I could program. Here I can only program the AND array part. So the product term generation can be programmed as per my requirement, but what I get, the functions that I can generate from this particular device would be fixed. Okay. So this looks like again. Yes. Traffic. Okay, 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 okay. Okay. So this is programmable array logic, PAL. So here you connect. So this way, here on the AND side, this is my AND array section. In this section, I am able to decide which product terms need to be generated, but my output is going to be F1 will be whatever the P0 is, which is generated. So P0 plus P1 only. It's always going to be this. I cannot change this part. And this is going to be P2 plus P3. In the previous case, I had the option of I could add more more functions F3, F4, and so on, as long as it uses whatever product terms are generated. I could add more functions at the output. So here I do not have that option. I will have to, I can only generate two functions, F1 and F2. Okay, it's fixed. F1 is always going to be P0 plus P1, and F2 is going to be P2 plus P3. There is no change possible in the OR section. So this is called a programmable array logic. And this is the most widely used programmable logic device. Though we do not have the flexibility to program the output section or the function generated, still this is preferred move. Okay, we give the flexibility to generate whatever product terms we want using the functions as and how we program it accordingly, but the end section is kept fixed. So this is what is largely used in industry. Now, so with that, we move on to sequential circuits. So we already, till now, what we were discussing were all combinational circuits. Combinational circuit is a circuit where the output only depends on what inputs you're applying. Suppose if I take a gate, an AND gate, I apply input 0 and 1. My output will be 0. The moment I change this input to 1, this changes to 1, right? My output changes to 1. Now this is not dependent on, okay, I applied 0 and 1 earlier, so it does not have any holding on my present output. My present output depends only on what inputs I apply presently. Okay, So those kind of circuits are what we refer to as combinational circuits. We saw a number of combinational circuits. Which were they? We had adders, subtractors, decoders, encoders, multipliers, multiplexers, demultiplexers. All those circuits that we saw were all combinational circuits. Okay, they only depended on, or the output only depended on what value of inputs you applied at that instant of time. Now, sequential circuit, what I mean by a sequential circuit is I have some kind of a memory. So, memory also, I had told you what sequential circuit is earlier. So, we spoke about if I enter a lift elevator, so I press button for the ground floor. So it keeps in mind which all floors request has been generated. So there is a memory which stores that, and it comes to the corresponding floor and stops there, right? So that we can enter and get down at whichever flow we want to. So there is some memory involved in that kind of a system. Similarly, if we talk about this room, okay, as if we consider that we have an automated system, that when a person enters this room, the first person enters this room, the light automatically turns on. Okay, so we can have a sensor for that, like somebody cuts the path of light, light sensor. Okay, so when you cut the path of light, some pulse is generated by the circuit and it keeps counting. So as people enter, it keeps a count of how many people have entered. So you're storing the number somewhere. And now I want the lights to automatically turn off as well when everybody leaves the room. Not when one person leaves, it shouldn't turn off. So that means again the circuit has to memorize, right? How many people are there, reduce the number, and accordingly, when the number reaches zero, only the circuit should switch off or turn off. So there, those kind of circuits, we have some memory involved. So now what do I mean by memory in digital circuits? What do I have to store? I have to store either a bit 0 or a bit 1, right? Bit 1 or bit 0, how do I store these bits electronically? How to store bits electronically? So now that means that if I have a value, it should always stay. If I store a 0, it should stay as a 0. I should be able to read that 0 always, right? Stored there. So now the simplest circuit or the basic circuit that we can have for that is a inverter, two inverters which are with a feedback. Okay, this is inverter, means what? Inverter is a NOT gate. So if I give the input 0 here, what is my output at this end? 1. Output of this one, 0. So is it the same? It keeps repeating, right? I gave 0 as my input. I'm not giving actually, because this is a feedback circuit, but as long as the input is, this section is 0, the output generated is also 0. That means I'm able to store a 0. So here I can store a 0. On the other hand, if the same inverter setup, I gave a 1 here, 1 inversion, 0, it becomes 0, becomes a 1 again. So this kind of a setup, if I started with a 1, I could store a 1, right? So this is possible here. But this circuit, this is the most elementary form of circuit to store, but I cannot use this circuit because here I have no control, right? I mean, it is like it's the circuit in itself is feeding the input. We are not giving an input from outside. Like you design a circuit, the AND gate, you decide whether you want to give a 0 and a 1 as the inputs. Here in this kind of a setup, I do not have a point where I can give an input and force the output to be 0. I want to give an input and say, okay, when I give this input, a 0 should be stored. Or when I give an input, a 1 should be stored. With this kind of a setup, that is not possible. We do not have a control from outside. So this circuit is not preferred. What we look into is I need to have what kind of circuits we use. They are called latches. Okay, latches and flip flops. Latches and flip flops, they are the basic circuits that are used to store memory. Memory elements, they're actually memory elements used to store information. Memory elements used to store information. Now, In the inverter that we saw earlier, in an inverter, what happens when I have an input 1, the output becomes 0. When the input is 0, my output becomes 1. So if I draw a circuit like I have my input and output, I call output voltage and input voltage. So when my input is 0, output is at state 1. And the moment my input switches to 0, my output drops to low. This is voltage. I'm talking in terms of voltage. Okay. So what happens is that this state is stable. This state is also stable. That is, when input is high, the output becomes 0 or close to low. And when input is low, in this case, the output is high. So this middle portion that we have, we call it a metastable state. Okay. So there is a sharp change, like the moment my input changes from 1 to 0, the system will try to go to one of the stable states, right? It has to switch from 0 to 1. The switching happens. So there is a lot of instability in this system, moving between 1 and 0, 1 and 0 continuously. Okay. So this is an unstable or unstable system. Okay. So to do away with this instability, we use latches or flip flops. Now, latch and flip flop, we'll first discuss about latches. And latch is a memory element which can store both 0 and 1. It can store a 0 also, it can store a 1 also. Inverter, as I showed you, either a 0 is generated or stored, or a 1 is stored. There is no combination where I can say I can store both a 0 and a 1. So when I use a latch, I can store both a 0 and 1 by giving certain inputs. Okay, so I can have, so I have two inputs here, which I call two inputs and two outputs. Okay, so there are, now a latch is also called a bistable device. We call a latch a bistable device because it has two stable states. 0 is one stable state, 1 is another stable state. So because it has two stable states, we call it a bistable device. It is also called a bistable multi-vibrator sometimes, because it vibrates from one stable state to the other. Okay. So we call it a bistable multi-vibrator as well. That is another term that we use. Now we have many number of or different types of latches that we can use. So we'll see the latches one by one. So the first type we have, I will first list out all the latch types. So we have SR latch, that is called set reset latch. Second one I have D latch, which is delay. Then I have JK, it is Jack and Kings, which we don't use normally. The terms JK is sufficient. Okay, we don't have to use more. And we also have another kind, which is toggle latch. Okay, that is T. T latch or toggle latch. Okay, T is the term. So we will be learning each of them, how we can use each of them to store data. Okay. Now, yeah, wait. Here itself, one more thing. Now we say that a latch is level sensitive. That means we call a latch as level sensitive. That is, the output of my latch will depend on the applied voltage level. Okay. What do I mean that? I mean, suppose if I'm applying inputs like this. Okay. So how long I apply a 1 or how long I apply a 0 will determine what my output will be. Okay. It is not the change from 0 to 1 which determines, because you can see these two portions. Here I have a change from 0 to 1, right? The signal changes from 0 to 1. Here the signal changes from 1 to 0. All those do not decide my output value. My output value depends or changes when I apply a specific input value for a certain period of time. So these levels of the input decides what the output is going to be. That is why it is called level sensitive. Okay. And okay, so that is about it. And now we have to talk about SR latch. We will discuss SR latch. So what a latch is a pair of cross coupled inverters. That means, sorry, cross coupled, not inverters, cross coupled NAND or NOR gates. NOR or NAND gates. Okay. So a latch is a pair of cross coupled NOR or NAND gates. What I mean by this is, if I have, you remember the first basic circuit that we started with this inverter setup. Okay. Now, in this setup, if I am going to replace each of my inverters with a NOR gate, okay, and I continue to keep the feedback. Okay, I continue to keep the feedback. That means I have to apply one more input. NOR has to have a minimum of 2 inputs. So let me apply an input here. I call it R, and I apply another input here, which I call S. Okay. So this becomes my, so I have converted this setup from a double inverter setup, feedback with feedback setup, to an RS latch. Now this, I'm just going to redraw the circuit again. Okay, I'm going to draw it this way. The same circuit. One input is R, one input to this is S. Okay. What is the other input? If I look to the circuit which has R as the, or the NOR gate which has R as the input, I see that the output of this gate, the second gate, okay, second gate is fed back. So this is 1 and 2 I'm calling. So this has to be fed back as input to this. And what about gate 2? What is the other input to the gate 2? Gate 2 has one input S, and the other input is the output of the first gate. So I again connect this like this. Okay. This output I call Q, and this output I call Q bar. Okay. So I replace the NOT gates in the initial setup with NOR gates. So when I have NOR gates, I have to have additional input. So now by applying appropriate values for R and S, I can force the output of the circuit to either 0 or 1. So I have a control now. If I want to store 0, I use a specific combination of R and S. Okay. And if I want to store 1, I use some other combination of input. So here you can force the output to a specific value by applying appropriate inputs at R and S. Okay. We'll see how it is done. I'm just giving the basic structure of this. Okay, till here, any doubt how we drew? So this is the standard form that we will follow. We will always draw the latch like this. Okay, whichever latch it is, we will be drawing it using this kind of a setup. Now, okay, so now let's see, let's apply inputs to this and see what happens. So I'm going to redraw once again. So I have my, okay, so for a NOR, what is the truth table? Truth table for NOR. If I have inputs A and B, my output is F. I get 0, 0, 0, 1, 1, 0. For NOR, the moment. So in NOR, the condition is that if any of my input becomes 1, my output will become 0. That is the control. Okay. So let me apply the first combination. S is equal to 1, R is equal to 0. And let me see what happens here. Okay. Going to apply the inputs. S is 1, R is 0. So the moment one of my inputs goes 1, what happens to the output of that particular gate? It will go to 0. That's what I wrote the truth table for. From the truth table, you know that if in any AND NOR gate, one of the inputs is 1, the output will be 0. So that means when I apply S is equal to 1, this output will be 0. Yes or no? Yes or no? Yes. Okay. So now this 0 is connected to the first NOR gate. So 0 and 0 input. So what is the output? 1. So when I applied this, I got Q equal to 1, Q bar equal to 0. This is correct. Q and Q bar means this is the complement, right? Q bar is a complement and it is working fine because I got Q as 1, now Q bar is 0. I'm okay with that. Now I apply the case S is equal to 0, R is equal to 0. Okay. So now let me change this S to 0 here. Okay. So when S is 0, you see here I have this 1 comes here, 1 and 0. 1 and 0, what happens? 1 and 0 means Q is 1, right? I'm looking at the second NAND NOR gate. Okay. Gate number 2. So here what is the input? S is 0. What is the other input? Q is the other input, right? Q is 1. 1 and 0 will give me what according to the truth table? It will give me 0. Now this 0, Q bar is the input. 0 and 0 will give me 1. So is there any change? No. So I'm getting Q equal to 1, Q bar equal to 0. Okay. Yes. R is 0, no? 0 and 0 according to the truth table, what does it give me? NOR. I never took, I initially applied S is equal to 1 and R is equal to 0. That's what I did. S is equal to 1, R is equal to 0 means what happens here? Okay. S is equal to 1. The moment S is 1 means, according to the truth table, if one input to the NOR gate is 1, this becomes 0. Now this I got the value 0. I will get the value 0. So this 0 I apply here. Then I get 0, 0. Yeah. I have to get 1. Then only I can get the other value. Okay. So then I got this as 1. And now when I applied both as 0, it continued to be the same value. Now take the next case. S is equal to 0, R equal to 1. S is equal to 0, R equal to 1. So R equal to 1 means, what is the output of this? This changes to 0. So for the NOR gate, the top NOR gate, since R is 1, the output automatically becomes 0. Now this 0 comes here, Q and 0 and 0, this becomes 1. Yes or no? Yes, Rhythm. If you apply, I will tell you why we are applying like this. I will tell you. Okay. Uh, so Q is equal to 0, R equal and Q bar equal to 1. One more case. Again, you apply S is equal to 0, R equal to 0. We have already applied that case, but we apply that case once again. Okay. So when you apply S is equal to 0, R is equal to 0, now what will happen? S is 0, R I make 0 again. My output is, yeah. So 1 and 0 is 0. 0 and 0 is 1. So Q is 0, Q bar is 1. So here, if you look at this first case, here I was able to, by applying S is equal to 1 and R is equal to 0, I was able to generate my output Q as 1. So here I could set output to 1. Okay. Then when I applied the case, both are 0, what happened? There is no change, right? This is the stage which we refer to as store. Okay, what happens here? Here it only retained the value which was previously at the output. My output in the previous case, when I applied S is equal to 1, R is equal to 0, I got my output Q as 1 and Q bar as 0. So this, after this, if I apply the case stage or the case where S is equal to 0 and R is equal to 0, whatever was my previous output, that output is retained. Okay, so it is similar to storing your output. What output was generated previously, that gets stored now. Okay, then I change from S is equal to 0 and R is equal to 1. I change to that. When S is equal to 0, R is equal to 1, my output is set to, what is my output now? Q is 0. So output is set to 0. And again, I apply S is equal to 0, R is equal to 0 case. I see that there is no change from the previous. When I applied the previous inputs, whatever output I had got, that same output is retained in this particular stage. So this is again no change, which is equivalent to storing data or retaining data. Okay. So this is how I can forcibly generate or produce an output 1 when I apply S is equal to 1, R is equal to 0. And if I want to store that for a longer period of time, my input has to be 0, 0. I apply input 0, 0. I can retain that output which I generated previously for any number of clock cycles or however long I want to. Okay. And similarly, if I want to force my output to 0, I have to apply the combination S is equal to 0, R equal to 1. And this will force my output to 0. And then if I want to retain that value for or store that value for a longer period of time, I again apply the combination 0, 0. Okay. So this way I can set my output to the desired value and I can store it using inputs, right? Here I have a control, what input I give. So as rhythm asks, initially giving 0, 0, actually it will always this, you cannot give 0, 0 initially to this circuit. You have to start with one of the methods in which I set the output to either 0 or 1. Then I apply 0, 0. Okay, you cannot start from 0, 0. Because then we say that the condition, I don't know what is the output. So the output is in some unknown condition, don't care condition, which I do not know. So I have to force the output to a known state, then continue to retain that. Otherwise, if I apply 0, 0, it will continue to be in that unknown state. I don't know whether it is 0 or 1, it continues in that state. Okay. So 0, 0 does not bring any change to the output of the circuit, in fact, and it retains the previous output. Okay. So this is how we are able to generate necessary output and store it also. So latch functions as a storage element. Yes or no? I can store a 0 also. I can store a 1 also. Okay. So now let's draw the truth table for SR latch. So according to the truth table, so when inputs are 0, 0, I should not get any change. No change. NC means no change. Okay. Then when it is 0 and R is 1, my output is Q is 0, Q bar is 1. 1 and 0, my output is it not? Yeah. So this is 1, this is 0. Now I have two more cases, 1, 1, which I didn't check for. Okay. Those two cases are invalid cases. Okay. What you get here is invalid. We will discuss that also. So these three cases, I hope you don't have any doubt in that. Okay. So let's also look at, before coming to the invalid case, let's also look at, I just showed you the implementation of an SR latch using NOR gates. I can also implement it using NAND gates. So NAND implementation, you only have to replace this with NAND. So I have some input. This I call S bar and R bar. Okay. The input now is S bar and R bar, not S and R and S. Okay, so there is that change that happens here. Only then. Now we'll just check for one case if the truth table works correct. Okay, so let's take the case when, let's take this case. Okay, S is equal to 0, R equal to 1. So S is equal to 0 means S bar will be what? I'm checking for the case S equal to 0, R equal to 1, which means S bar will be 1 and R bar will be 0. Okay, this is the case we are checking for. So S bar is 1, R bar is 0. So NAND gate truth table, if I draw NAND truth table 0 0 0 1 1 0 1 1. So according to the NAND truth table, what can I say from the NAND truth table? Which is the controlling input, or if one input is set to some particular value, I can generate a particular output. Which is that controlling input for a NAND gate? 0. So the moment I have a 0 as one of my inputs, my output will always be 1. Okay. So according to that, so I see that R bar is 0 means this output is going to be 1. Okay. Now 1 and 1 come here, I get 0. So that means, so what is my Q? Q is equal to 0, Q bar is equal to 1. This is the same as the truth table I wrote here for SR. I mean, using NOR, I had written the truth table. The same thing is applicable here, yes or no? The condition is satisfied here also. So you can check for other conditions as well. It will get satisfied. Okay. Now we have a problem with 1 1. So let's see what the problem with 1 1 is. Okay. So, like the previous case we checked for, what was the previous case we looked at? We looked at the case where S is equal to 1, R is equal to 0. So, when S is equal to 1 and R is equal to 0, I mean, S bar is equal to, S is equal to 0. So, I got 0 and 1. Now, if I make this 1, okay, I'm making this 1. Now, I'm checking for the condition S is equal to 1, R equal to 1. Okay. So 1 and 1 comes, I should get 0. 0 and 1 comes. Sorry, not S is equal to 1. S is equal to 1, R is equal to 1 means now this condition is S bar is equal to 0, R bar is equal to 0. Okay. So both become 0. Okay, both are 0. Okay. So what is the output going to be now? both will be 1 1. Okay, any doubt in that? It will, because 1 and 0 will give me 1 for the top gate, and 1 and I mean the 0 and 0 would also give me a 1. Okay, so now I get q equal to 1 and q bar is equal to 1, which is contradictory to each other, right? I cannot have q and q bar the same, it has to be complement of each other. So this way, now if I again try to apply a 1 1 there, what happens? 1 1 becomes 0, 0 and 1 also becomes 0. So when when I mean s bar is equal to 1 and r bar is equal to 1, what is the value of my s and r? S is 0, R is 0. And S is 0, R is 0 is a condition where I should retain the previous value, right? Wasn't it for storing? So this condition was for storing. When S is equal to 0, R is equal to 0, whatever is what was the previous output should be retained. But now here, when S is 0, R is 0, it implies that S bar is 1, R bar is 1. But if I apply R bar and S bar as 1 and 1, I get my outputs now as 0 and 0. That means there is no retention also, no storing also happening. So after that, if I apply some input. So this is a case which we have to avoid in this case. I should not apply the inputs 1 and 1 to the latch, SR latch, okay, whichever combination that I'm using. So this is why we say it is an invalid condition, because it is giving contradictory output. Okay. Now, see, there is one more thing here, that I am applying these inputs. I say that, do you think that my outputs, that is Q and Q bar, is going to be generated at the same time? In theory, we would like to say that yes, but each gate is not identical. Though it is the same NAND gate, two input NAND gate that I use, though the NAND gates are manufactured using the same technology, but there will be an inherent variability in them. Okay, there will be a small amount of difference in the NAND gates. So never will I be able to generate both outputs at the same time. Okay, each gate will have very minute difference. I mean, it is not something that we can say as a large or quantify it as a large value, but there will always be a small difference. Okay, a single two gate circuit is fine, but when you have large circuits, it accumulates, the delay will accumulate, or that there will be a difference in the time taken or the propagation delay of each gate, though it is of the same functionality, will not be the same. Okay, that is also there. Okay, now if I want to extend this design of an SR latch to having a gated latch, I can have an enable input also. That is, only if the enable is high, the circuit works. And if the enable is low, it stays so. So that I have that kind of a circuit also. It's called a gated SR latch. So here we have an enable input E. Okay. So when E is equal to 1, the latch is active. When E is equal to 0, the latch is deactivated. Activated, and the output does not change. Whatever previously, if you had an output, it will stay that. Okay, an output does not change. Okay, so let's see the circuit for that. Okay, so here what happens if I have the enable signal as 0, then it is going to be in no change condition. Okay, so irrespective of what the value of my S and R are, it is going to be that. That is because again in a NAND gate, so this part does not work in that case. And now when I apply the inputs, once it is 1, what happens when it's 1? When enable is set to 1 and my inputs are 0, 0, it should be the same. It should be the storing or retaining state. So I say no change there as well. The moment S is 1 and R is 0, if enable is high, then I should get Q as 0 and Q bar as 1. It is the same truth table as the previous one, just that here you have an additional input which decides whether the circuit is going to give you a change in output or not. Okay. So if it is 0, there is no change. And if it is 1, depending on the conditions or the input combinations that you're applying, we will get a specific output. All right. And 1, 1 again is invalid case, which we shouldn't consider here. Okay, so suppose if I give that S is 1, R is 0, and enable is 1. Let's check for one condition. Okay, so 1, 1, 0. This is what comes here. What is this? What will be the output here? 0 and 1, what gives me the output for NAND gate? What is the output of a NAND gate for 0 and 1? 1. Okay, so, okay, now this part was, this becomes S bar R bar, yes or no? Because S I gave 1 and 0. I generated 0 and 1 here. Yes, if you see the first stage, when I applied S and R as 1 and 0 and my enable was high, I'm able to invert my S and R at the output. Okay, so it's actually inversion that happens here, okay, using this stage. But it is a controlled inversion. Only if my E is high, this is going to happen. Enable is high. Now, so now this becomes like the normal SR NAND latch that you learn. So 0 and 1, if I do here, if one input is 0, my output will be 1. 1, 1 will give me 0. Right? Yes. So it satisfies this condition. This is the condition that I applied. Enable, so enable is high, S is 1, R is 0. So the moment that is done, I'm generating the output Q and Q bar. So this corresponds, this section corresponds to my SR NAND latch. And this is actually the control that I have. Using the enable, I'm able to invert my signals using this first section. Okay, is that clear? So I have another alternate design. I can use NOR also, right? Alternate design for SR latch. See, in the NAND implementation and the NOR implementation, the difference was that in NAND, I will have R as, if you see, this was NAND, I had S will be S bar and R bar. That is the way I have to write. I will go previous. So S bar R bar is for the NAND implementation. This is how it should look. And if I had the NOR implementation, it would be R and S. Okay, so the way you give your inputs is also important. Okay, it's not that I can randomly give R here and S there. It's not the same for both implementations. So keep that also in mind. Otherwise, we will not get the desired output. So here, if I want to have the same gated implementation using NOR, then I will have to use, this is the way I have to do it. Okay, I don't need a NAND gate initially. Instead of that, I can have an AND gate. You can verify the truth table if you want to see if it is working. Okay, that is an exercise that you can take up on your own. Okay. Okay. Now, did you people do? I had given one question to do. Did some of you do that? That design a 4-bit adder subtractor using full adders and mux. Anybody who did? No, nobody did. Good. As building blocks. Okay. So So I will just discuss that part before I discuss D latch. Okay, here SR latch is done. So this is the way we have SR latch. So SR latch is used, how we can use SR to store a 0 and a 1, and how I can retain that value, everything. How I can generate a 0 and a 1 and also store that value. Okay, what combinations I should use, what combination should be avoided is all given to you. Okay, 0 0 is to store, 1 1 is the invalid combination which we shouldn't use. So any other combination, s is equal to 0 and r equal to 1, gives me my output, as forces the output to 1. And if s is equal to 1 and r is equal to 0, I think no, 1 or 0 generates 0, I think. S is equal to 0, r equal to 1, output is 0. And s is equal to 1 and r is equal to 0, output is 1. Okay, so this way we generate the necessary outputs. Is that clear? The concept is the same for any latch that we will do. There is no change in that. Okay, the next latch we have to look into is D latch. Now, this question, do you want me to give the circuit for the question that I had given last class? I mean, if you want. So anyway, I told I will give, so I'm giving. Okay, so it is a adder subtractor using full adders and mux. That was the question. Okay. So what does my full adder circuit actually look like? I already had, this is my old circuit which you have learned. 4-bit adder I have inputs A0. I'll give A0 there. So let's see. If I have to give this input, I have XOR. This is the old circuit you need not do. I am just showing so that I so S is equal to 1 means it will be subtract, and S is equal to 0 is add. So I have outputs. Okay, you don't have to draw this. This is what I have to implement. I'm saying that I have to implement this, but I cannot use these XOR gates. I have to replace the XOR gates, and I should have what over there? Mux. Okay, I should use mux and generate. Okay, so let's see how the circuit will look like in that case. I'm going to draw it like one more breakup I will do. This is a full adder 0. Okay, let's start. This is the same thing I'm doing. Okay, I'm drawing the old one and I'm breaking it up into 1-bit full adders and drawing. So no talking here. Okay, those who want to talk, please go outside. So B3, A3, and I have connections. So C1, C2, C3. Let's draw that. This C out. I get some S0, S1, S2, S3. I don't know for exam for carry look ahead at many of you had written so many inputs A3, B3, A2, B2 and all that. And finally, you have only one sum bit. For adding 4 bits, you have only one sum bit. I don't know how it works out, but many of you had done that kind of a thing. Okay. So now this I'm going to replace with what? This portion I will replace. How will I replace? I can use a mux there, okay? 0 and 1. That means 0 means I have to do normal addition. That means for 0, I apply B0. Okay, wherever the mux is there, the other one will have one input. The select, I mean, I have to, the select line is going to be this control signal will be my select line. And here, if this is 1, it has to, so when S is equal to 0, B0 will pass as it is. When S is equal to 1, B0 bar will come, right? For subtracting, I need to take the complement and then do, right? 2's complement addition, right? So, and I also have to connect this to this. So same way here also. So you replace all the XOR gates with a mux. So when the mux select line is 0, your input should be the number, unaltered number, B0. I'm just going to add. When S is 0 means I'm supposed to do addition, which means I add A0 with B0. So to that input position 0, I give B0. And when S is 1, select line is 1, I have to perform subtraction, which is 2's complement subtraction. So I need to take the complement, 1's complement. That means I need to invert the number. So I give it to this NOT gate, and I also have to add C in. Okay. Right? I have to add that. That is the same as the previous circuit here. My C in was from select line. So same way I do it. Okay, so replace this. That is the only thing you have to do this. Okay. Okay, we'll stop.